Welcome to the next video on circuit protection. We're going to look at three-phase protection devices, and we're going to look at devices to deal with short circuits, undervoltage, overvoltage, overload or overheating, loss of phase, phase reversal, and auto restart. So three-phase miniature circuit breaker construction. This is obviously a single phase circuit breaker. A three-phase miniature circuit breaker has three sets of what you see here, side by side, connected together. As a result, it has a base with six external connections and a reset lever that's joined across all three. There's obviously three sets of contacts, three arc chambers, three thermal bimetal strips, three magnetic trip coils, and last but not least, three latch tripping mechanisms. So three-phase circuit breakers are basically the same as single-phase circuit breakers. They have the same protection for each phase, but there's three of them. Each phase is protected with a thermal protection circuit, which has a bimetal strip, and it also has a magnetic overload with a solenoid. They're joined together as a single unit, and if you have a look here in this photo, there's a tripping mechanism which is common to all three. So how does a three-phase circuit breaker operate? The first thing is, if there's a fault in any one of the phases, all three are tripped together. And as you saw in an earlier slide, there's that bar that goes through the middle of the circuit breaker that connects all three trips together. So if you have an overload current in one or more bimetal strip, the bimetal heats and starts to bend, and eventually, if it's maintained, the overload is maintained, the mechanism will be tripped and the circuit breaker will stop the current flow. At this point, there's not enough magnetism in the electromagnetic trip mechanism, or the solenoid in this picture, to cause the trip to happen. But if the fault is more severe and short circuit current flows, then definitely you're getting enough magnetism for the solenoid to pull the mechanism open, and the circuit breaker will trip very quickly. If there's a lot of current in the fault, there will be a lot of arcing, and the arc chamber draws out and quenches any arcing to deal with that. Once it's been tripped, the latch stays open, and you will need to find the fault and fix it, and then reset the circuit breaker manually to reliven the circuit. Undervoltage protection. You think, well, why do you need that? Well, in some circumstances, not enough voltage driving a motor, for instance, is as bad as too much. So there are different solid state or electronic relays that will switch off when the gate voltage falls below a set level, and that will stop the equipment from working. There's mechanical or electromechanical versions as well. Moving iron relay here, you can see in the middle, and it does the same thing. When there's not enough voltage to produce enough current to hold the magnetism in the coil, the relay drops out. And these days, soft starts and VSDs incorporate all this sort of stuff inside. They're pretty amazing machines these days. They can be programmed very highly, and they come with all sorts of different protections built in, and they will have undervoltage protection in them as well. The opposite side of that, overvoltage protection. Small overvoltages, it says here, 10% of the normal supply are enough to cause a motor to draw more current than it should, and you're going to end up overheating that motor and burning it out. It's going to cost you money. So you need to protect from overvoltage. There are overvoltage relays once again, and also VSDs can incorporate overvoltage in their software as well. Overload protection, it's pretty important, and there's four that we're going to discuss: magnetic overloads, thermal overloads, thermistors, which are temperature sensing, and of course the integral VSD overload protection. Did I say what VSD stands for? variable speed drive. Here we have a magnetic overload, and we'll look at its construction. It's got a plastic case on the outside, obviously, and terminals to connect wiring to it, and it has also terminals and prongs to connect the three phases for the motor supply to a contactor. The overload itself doesn't switch the motor on and off, it controls the contactor, which in turn switches the motor on and off. It has three current coils, as you can see in the bottom middle there. It has contacts, control contacts on the bottom left, trip control circuit and circuitry on the right, and trip and reset mechanism in the top of the overload. So how the magnetic overload works: it has three sensing coils that sense current. As the current increases in the circuit to a level that is dangerous to the motor, the magnetism developed, it then operates the contacts via the control circuit. The control circuit prevents tripping during startup, because we know that a motor draws high current, 6 to 9 times full load current, when it's starting up, and if we didn't deal with that every time the motor started up, this would trip out. So we have to have an electronic control circuit to stop that and to time it until the motor is started. Once the overload has been tripped, it can be set to either manually be reset or automatically reset. Then we have a similar sort of thing, a thermal overload. It just works slightly differently. It has different advantages and disadvantages. It has, once again, plastic body with external connections on it. It has three bimetal strips and heating elements for those strips. It also has a trip mechanism that when one or more of the bimetal strips bends, the mechanism is tripped and the contacts open or close. So with the thermal overload, like we said in the last slide, sustained overcurrent or a short circuit in one or more of the phases heats the bimetals, and the bimetals bend. Eventually they bend far enough to operate the contacts of the control circuitry. It has to be, once again, they can usually be reset manually or automatically after cooling. The thing with thermal overloads is, because it's heat that's bending the bimetal, it takes a while for the bimetal to cool down again and be ready to be reset. So there is a bit of a time delay there, which can cause an issue. On the other hand, you don't need timers and expensive electronic parts to this. It's simpler to make because the bimetal doesn't heat up fast enough to trip on startup of the motor, so it automatically copes with the startup of the motor. So now we'll have a look at thermistors. Now, thermistors are a small electronic device that, like I said, senses temperature. The materials they're made out of gives a sharp rise or drop in resistance depending on which one you have at a specified temperature. So this change in resistance can be used to control the circuitry, and it might be wired up to a VSD, and the VSD monitors the thermistor. If it sees a change in state, it knows, oh, this motor's hot, and will shut it down. If you have one phase lost in a three-phase motor, you have the other two phases trying to cope with the load, and the current increases, the motor runs badly, and it may burn out eventually. So we use phase failure relays to detect the loss of a single phase and open the contacts so that the current stops flowing to the motor. Next is phase reversal, and it's important that a motor goes the right way, in particular a three-phase motor, you might want to use a phase reversal relay. Why would you need one of these? You've probably covered three-phase motors by now and know that it is really easy to make them go the wrong way or go change direction. All you have to do is change over two phases. There's a whole variety of reasons why or how two phases could get changed over depending on the circumstances. One might be that someone's crashed into a pole out in the street, and when the power supply authority come and replace the overheads, they somehow cross two phases over to where they used to be. There's a whole bunch of reasons. So if it's important that motor goes the right way, you should use one of these phase reversal relays. Auto restart. If you have some sort of machinery like the saw bench in the picture here, and the power goes off for some reason, and then the power comes back on, if in the meantime the saw has stopped and it suddenly starts up again without any warning, you never know what the circumstances might be. We might be touching the blade, might be leaning over the saw bench, not expecting it to start up again. It could be quite a dangerous situation. So the wiring rules require us to protect against dangerous restarting. And if you have a look at 4.13.1.4, you can see there what it says about protecting against restarting or reversal of motors. Okay, that brings us to the end of this video on circuit protection.